Cool. All right, we're very happy to have Adrian Bayer here. So Adrian did his master's at Cambridge, I believe, and then I went over to Berkeley as got his PhD under Orosh Seljak, and then came over to the East Coast I guess this year in the fall, and he is at Princeton in Simons. So spends Monday, Wednesday, Fridays, just 20 blocks up north at the Flatiron Simons Foundation. So Adrian's going to tell us a little bit about neutrino masses, field level inference, and voids today. So without further ado, go ahead, Adrian.
Cool. Hi, everyone. Thanks for the introduction, David. So yes, I've been asked to speak a bit about my work on measuring neutrino mass in cosmology and also field level inference. Just as a disclaimer, I haven't applied field level inference to measure neutrino mass yet, but I'm going to tell you about the journey that we're working on to do that. So just to give an outline of my talk, I'll start by giving an overview of how we can measure the neutrino mass up to today using particle physics and cosmology. Then I'll talk about some of my work in measuring neutrino mass from the nonlinear cosmic structure. So going beyond linear theory, how much information is there in the cosmic structure. Then I'll talk about the HalfDome simulations, which are these big simulations I'm working on building for joint analysis of CMB cross LSS for stage 4 surveys. Our first paper and data release is on the way soon. But one fun thing we've done with these already is measure something called the supersample covariance, which I'll tell you about. And then finally, I'll talk about field level inference as a way to optimally extract information from cosmological data. But starting with how to measure neutrino mass, let's go to the particle physics lab to find out what the mass of a neutrino is. So this is a picture of me many years ago when I used to be a particle physicist. And let's ask the question, how accurately can we measure the neutrino mass? Well, the first evidence for neutrino mass were neutrino oscillations, and this is the observation that different flavors of neutrinos can oscillate between one another. And one piece of evidence for this was the atmospheric neutrinos, where cosmic rays interact with the atmosphere. That produces muon neutrinos, but then once they travel through the Earth, they change flavors. You don't observe as many muon neutrinos as you would have expected. And then there's also the solar neutrino experiment, where the sun is a nuclear reactor. It does beta decay, which produces electron neutrinos. But when you observe the neutrinos on Earth, you don't observe as many electron neutrinos as you'd expect, which implies that these neutrinos have changed flavors. And if neutrinos can change flavors, that means that they have mass. And so based on these two experiments, you can draw these two hierarchies of what the neutrino masses are. You have the normal hierarchy, where the two very light neutrinos and one heavy neutrino, and then the inverted hierarchy, where there's two heavy neutrinos. But neutrino oscillations only tell you about the difference in the masses between the different mass eigenstates. It doesn't tell you what the absolute scale of the masses are. So this gives you a lower bound on the neutrino mass of 0.06 eV. If you want to actually measure the absolute scale of the mass, of the neutrino mass, then you go to beta decay, and that's what the Cation experiment does. So in beta decay, you have a neutron which decays into a proton, electron, and an electron antineutrino. And because this is a free body decay, if neutrinos have mass, that leaves an imprint on the energy distribution of the electrons. It will take away some of the energy of the electrons. So what you can measure is what the maximum energy of an electron is, and depending on how heavy the neutrino is, that will shift that tail of the distribution. And so the Cation experiment currently has a upper limit now of 0.8 eV. It's forecasted to go down further soon, but that's where we are right now in terms of beta decay. And so what we have from particle physics is this range of scales. Oscillations telling us that the lower limit is 0.06 eV, the beta decay experiment telling us 0.8 eV, and cosmology can help us bridge this gap and get closer to actually measuring the neutrino mass. And the way cosmology can do this is, here's a picture I'm sure you've seen many times of the evolution of the universe. The first way to measure neutrino mass using cosmology is using the CMB. So light from the CMB travels through the universe to us today, and if there are massive neutrinos in the background of the universe, then they'll get picked up in the CMB through, for example, the Sachs-Wolf effect, and that will leave an imprint on the temperature and polarization of the CMB. And Planck measured this in 2018 and got a measurement of 0.26 eV. So already pushing down the upper limit close to the 0.06 eV lower limit. But another thing neutrinos do, which is very important, is it changes the clustering of matter in the universe. So cold dark matter tends to cluster to form halos, which is where galaxies form. But neutrinos are very, very light, and so they're very, very fast, and it's much harder for gravity to make them cluster. So they tend to just whiz through and not cluster. And so adding information about clustering, for example, from BAO, baryon-acoustic oscillations, further pushes this limit down to 0.12 eV. And so that's where we are with Planck and BAO, 0.12 eV. So very close to this 0.06 eV. But this is based predominantly on linear theory, so the linear scales. But if we could push to even smaller scales, then we could get even tighter constraints for neutrino mass using cosmology and really reach this low bound. And so, in response to the initial question, how accurately can we measure the neutrino mass? This is the advice I was given, not really.
What experiment are you doing here?
This is actually a LZ, so it's dark matter related experiment. But yeah, so yes.
You mentioned the Catron experiment is like at 0.8 eV, and you said there's room for improvement.
Yeah.
Do you know like what's the progress on that? Like how close can they get?
So their forecast is 0.2 eV. They hope to get to by the end of observations, and I think that should be like coming around pretty soon.
Okay.
Yeah.
But that still will not be good enough potentially to match cosmology.
So yeah. So compared to cosmology, it would be very similar to Planck 2018, but when you add the large scale structure and you add a BAO, you're still not competitive with that.
Yeah. Well, and also cosmology is all flavors.
Right.
Catron is just
the
one flavor.
Yes.
Yeah. So you want to get the fraction of the E, which is in the heavy states.
Yeah. So in a sense, it's different measurements and they're complementary. Yes. Cool. So rewind fast forward the clock 9 or so years, and here we are in terms of cosmology. We have a lot of experiments coming out soon, already up and running, both in terms of large-scale structure. These are going to probe smaller and smaller scales, more nonlinear scales, where neutrinos have the biggest impact. And then we also have CMB experiments, also probing smaller scales and measuring CMB secondary effects like the TSC, the KSC, and CMB lensing. And so if we want to study this data, we need a way to model neutrinos. And the effect of neutrinos is very well understood within linear theory. It has this damping of the power spectrum on small scales. So as you increase the neutrino mass, there's less clustering on small scales, and so the power spectrum decreases at high K. But the problem is small scales are nonlinear. So if we want to analyze all this new data on very small scales, we need a way of modeling neutrinos in a nonlinear regime. And so to do that, we can use n-body simulations. So an n-body simulation, just to give an overview, typically you just put in dark matter particles and you let them evolve under the equations of gravity, and it gives you some distribution of matter. But if you want to include neutrinos, it becomes complicated. You can put in extra particles corresponding to neutrinos, but this actually turns out to be quite difficult because neutrinos are very fast. It leads to a lot of short noise in the simulation. So people have come up with various ways to bypass this. For example, Yassine had a method back in 2012 which didn't put in the neutrino particles and just put the effect of neutrinos on the dark matter clustering in the n-body simulation. But there are also ways of doing particle simulations and reducing this short noise, which I won't get into. But at the end of the day, what you get is some nice three-dimensional distribution of the neutrino clustering over here and the cold dark matter clustering over here. And you can see that the dark matter clustering is a lot finer, a lot more structure, whereas neutrinos is more sparse, less clustered. And then when you add them together, you get the total matter distribution, delta M. And so now that we have these simulations telling us about the nonlinear distribution of matter with neutrinos, we can analyze this and look at how much information there is about neutrino mass in this structure. So let's start by looking just at delta M, so the total matter density. If we want to analyze nonlinear data, we have to move beyond the power spectrum first of all. So earlier I showed you the power spectrum, which would give you all the information there is in the linear case. But if you move to a nonlinear structure, then the 2-point information, the power spectrum, no longer gives you everything. And so one way to get more information out of a field is to use higher order statistics. And two such higher order statistics that you can use is the halo mass function, which looks at the abundance of halos as a function of their masses. And also the void size function, which looks at the void, the size of voids. The abundance of voids is a function of their size. And we found that if you combine all these different statistics, they have very different degeneracies in the mu sigma 8 plane. So that when you combine them all together, you get a really, really small contour on the neutrino mass when you go to K max of 0.5. And this is for a volume of 1 gigaparsec. But the key point is with the 2-point correlation function, you get this red contour, whereas when you combine everything together, you get a really, really small contour. So it looks like there's a lot of information about neutrino mass in the nonlinear large-scale structure.
Is the halo mass function giving you anything at all at that point?
So it does give a little bit, but yeah, predominantly this is coming from the 2-point and the void size function. But yeah, there's a small increase from the halo mass function here as well. And so one really interesting thing here is if you look at the power spectrum on its own, you look at the error bar and the neutrino mass, it saturates at around k of 0.2, k max of 0.2. So you could keep probing smaller and smaller scales, the power spectrum isn't going to give you anything more. However, when you combine with these different statistics, so for example, if you just combine with H, which I guess is the question you just asked, you do get a decreasing line, and if you combine all of them together, you still get a decreasing line up to k max of 0.5. So this is saying you can go to smaller and smaller scales and get more and more information about neutrino mass when you include this higher order information. But things to keep in mind is we're looking at the matter field here. In reality, we measure halos or weak lensing. Also, this is just looking at a single redshift. If you combine multiple redshifts together, you could potentially get even better constraints. There's also a supersample covariance effect, baryonic effects, and systematics that need to be taken into account. And I'll go through some of the things on this list in the remainder of my talk. Another exciting thing you can do in terms of measuring neutrino mass is why still for halos and voids. You could also look at other parts of the cosmic web, like filaments and walls. And so in this project with James Lansiri, who's a graduate student at Princeton, what we're doing is splitting the cosmic web into these 4 different environments. Then you measure the power spectrum in each one individually. And then when you combine and cross-correlate different power spectra in these different environments, you can also get much tighter constraints on neutrino mass than if you just looked at the total power spectrum on its own. So comparing the black contour to the white contour.
So what are walls?
Walls are like 2D. So you think of halos like 0-dimensional like points in a sense. Filaments are 1-dimensional lines.
Right.
Walls are like these 2D structures in the universe, and then voids are just emptiness. And mathematically, the way you define it is you can just take the Hessian of like your tidal field or your density field and look at the number of eigenvalues which are positive or negative. So there's many ways of many high order statistics that you can use, and I stopped updating the slide in 2021, so there's much more now. But you could look at lensing, look at the bispectrum, Minkowski functional, peak counts, probability density function. You can look at the matter field and measure the probability density function. You can look at redshift space, the bispectrum, Mach power spectrum, wavelets, voids. So there's this huge list of papers reporting all very tight constraints on neutrino mass, some even better than what I've shown you already. But they all look at something different, a different statistic, a different field. And so a very important question to ask is, where is the information coming from? If we actually want to go to surveys and measure the neutrino mass, it's important for us to know what is giving us this information about neutrino mass. So to start this off, before we were looking at delta M, and we saw all these different degeneracy directions, I've also added the Mach power spectrum here, which is this black contour, which gives really tight constraints. This is like the power spectrum, but it's downweighted in certain areas depending on how empty they are, so it kind of folds void information into the power spectrum. And then also the linear power spectrum in yellow. So you can see all the degeneracies are completely different. And so that's why there's so much information in delta M. But if instead you looked at delta C, just the CDM density, all the contours align. And so what this is telling us is that there's actually not that much information in delta C, and most of the information in delta M is coming from delta nu and these F nus. And so the next question to ask is, what do surveys actually measure? So surveys don't measure delta nu. If they did, we'd have amazing detections of neutrino mass. They also don't quite measure delta C. They measure halos of galaxies, which in linear theory is just related to the CDM distribution with some bias parameter. And they also don't measure delta M. We measure lensing, which is an integral over the line of sight of delta M. And then the key point is it's multiplied by this omega M factor. And so the question we wanted to answer is, when you look at these fields, how much information is there about neutrino mass? And so to do this, we ran 2 n-body simulations with the same linear physics, one with massive neutrinos, which we called the real simulation, and one without massive neutrinos, which we called the fake simulation. And the key point is the linear physics is matched. So any difference between these 2 simulations imply that there's some difference in the nonlinear structure, which is due to the presence of the massive neutrinos. And what we found is when we're taking the cross correlation between these two fields, the matter line, the green line, goes away from 1 at around k of 0.1, which is showing that there's some difference in these fields due to the nonlinear physics. But when you look at the halos or the lensing, actually the cross correlation stays 1 almost to k of 1, which suggests there's not that much information when you look at the halos or lensing field at the field level. So the nonlinear effects of massive neutrinos at a single redshift can be faked by CDM for halos and lensing.
I'm just confused. I'm not 100% clear on how I read this plot.
So you have 2 fields generated from these 2 simulations.
Good.
You take the cross correlation coefficient.
I see.
And so if it's equal to 1, that means the fields are perfectly correlated with each other. So the phases of the 2 fields are identical. And it's the phases which tell you about nonlinear.
And what's the M line?
M is pure matter. So before we had delta M, we had delta C and delta nu, and then I motivated that halos are kind of related to delta C, and lensing is related to that integral of delta M. And so M is just pure 3D matter. So if you could measure the 3D distribution of matter, you'd get the M line. But if you look at lensing, which projects that down to 2D and has its own M degeneracy, or if you look at the halos at delta C, then it kills up most of the information.
So you can't measure that green line directly, right? So you
Yeah, you can't measure the field responsible for the green line. Yeah. But this is just at a single redshift. And so moving forward, how do we maximize the amount of information about neutrino mass? First thing is to jointly analyze multiple redshifts and multiple traces. So neutrinos evolve differently to dark matter. So even though at a single redshift you can match things and dark matter can give the same effect as neutrinos, if you combine information from different redshifts, you can get tight constraints on the neutrino mass. And the prime example of doing that is combining CMB with LSS. CMB happened very early universe, LSS very late universe. And there are some forecasts on the neutrino mass when you combine CMB S4 with LSST, sharing clustering, you get this orange contour, which gives around 0.02 EV constraints on neutrino mass. And you can see that that's much better than if you just did LSST on its own, these blue and pink contours. So combining with CMB helps tighten constraints. Second thing you can do is use velocity information. So velocity is a trace of the total matter density. So if you can somehow measure velocities, that will give you information about neutrinos. And this plot is showing that if you look in redshift space, you see distortions along the direction along the line of sight. And so when you compare the power spectrum of the real simulation and the fake simulation from the previous slide, there's a signal along the line of sight. So if we have better modeling of redshift space distortions or peculiar velocities, for example, from KFC, from supernovae, and from fundamental plane, then that will also give us more information about neutrino mass. And then finally, one can develop statistical methods to optimally extract information. So instead of using power spectra or halos or voids, there's this method called field level inference, where you try to take all the information from a cosmic field and get optimal parameter constraints. And so in the remainder of my talk, I'm going to go through these 3 different points and how that can help measure neutrino mass and work that I'm doing each of these 3 things. So let's start by talking about combining different probes. So if we want to combine different probes like CMB and large scale structure, we need to understand the physics all the way from the CMB to the large scale structure, understand the systematics that are going on in between in a correlated way so that we can do this analysis. And so to do that, and yeah, I should also say that what I'm going to talk about now is moves beyond just neutrino mass to actually help measure all the different cosmological parameters like S8 and H0, where there's some tensions at the moment, dark energy, and primordial non-Gaussianity. So we're measuring the universe in many different times, many different probes, with CMB, big lensing, like alpha, galaxy surveys. And we want to be able to combine all of these when we do our analysis. And if we want to do that properly, we've got to ideally have a simulation which takes us all the way from the CMB down to the large scale structure, including everything in between, so that everything's correlated and you can run your analysis in a correlated way. And there are also secondary effects caused on the CMB, for example, due to the correlations between different probes. For example, light from the CMB has to travel through all the matter on its way to reaching us, And so it will be lensed by the same matter, which is responsible for galaxy clustering and big lensing. And so everything in this whole story is correlated. Another thing where the CMB interacts with large-scale structure is in kinetic SC, where photons from the CMB interacts with fast-moving electrons, and that changes the energy of the photon in a way that's dependent on electron velocity. So this is also very interesting in terms of neutrino mass, because this is dependent on velocities, as I said in the last slide. That's just one for neutrino mass. And so what we want is a way to simulate all these things. And then another key point is systematic. So when you measure the CMB, you're looking at this particular part of the electromagnetic spectrum. This plot is showing all the cosmic backgrounds, all the radiation coming from cosmology. And there's the CRB, the radio background, and the CIB, which leak into the cosmic microwave background. And just to give you an idea of what these things are, CRB is based on synchrotron emission, and CIB comes from dust. And these emissions cause problems when we're trying to measure the CMB. And for upcoming experiments, which are probably really, really small scales, we need a way to understand all these different parts of the spectrum. And so what we want to produce is this simulation which simulates everything, all the physics, all the systematics, so that we can go out and analyze the data accurately and really push to the smallest scales. And that's what we're trying to do in this HalfDome collaboration. We're trying to build these big simulations of the universe. And I'm going to tell you about that now. So let's look at what's on the market already in terms of the CMB community to do cross correlations with LSS. So let's start by looking at the stage 4 requirements. So for stage 4 surveys coming out over the next decade or so, what you need to do an accurate CMB cross LSS is you need a box size of a few gigaparsec over H in order to get the lensing correct. You also need a mass resolution of around 10 to the 12 solar masses over H in order to get the CIB, the infrared background, correct. You want to simulate all the different large-scale structure observable, so big lensing, galaxies, and clusters. And ideally, you have a few realizations to get error bars on everything. And so in terms of what already exists, this is how everything matches up. So nothing quite ticks all the boxes. One key point is that all the simulations so far just have one realization. And so with HalfDome, what we're trying to do is build a simulation which ticks all the boxes for stage 4 survey. So we have a 3.5 gigaparsec box with 644 cube particles, minimum mass of 10 to the 12, and we're including all the different weak lensing and galaxy observables. And currently we have 11 of these simulations, and I'm making more.
What's the difference between each simulation run? Like, what do you change exactly?
You mean, in the 11?
Yeah.
So the initial conditions, so the random initial conditions. So when you start an embodied simulation, you've got to give it some initial conditions. You have some power spectrum, which is well defined by whatever the physics is, and then also the phases. And so those phases are random. And that's something you've got to marginalize over when you do the spectrum analysis.
So you've done 11 so far, or?
Yeah, 11 realizations with different phases, yeah. Plan is to do more, but moving on to the next slide, even 11 is a 1000% increase in the number of simulations. And this is really like a big computational challenge. So we ran these on the Cori supercomputer to start with. Cori was actually, when it came out in 2017, ranked as the number 5 most powerful supercomputer on the top 500 list. So it's a really powerful supercomputer. And to run these simulations, we had to use up half of Cori, which is really huge. And so that gives you an idea of how expensive these things are to run. Then we eventually moved on to using the Stampede supercomputer because Cori shut down like last year or 2 years ago. And we also use this fast embodied simulation called FastPM, which also helps make this, you can run each simulation in just a few hours. And altogether, we have 3 trillion particles, 300 terabytes of data, and it's all stored at NERSC, which was the home of Cori. So yeah, the real challenge in producing more than 11 simulations is finding storage for this stuff, rather than running the simulations themselves. And this is also made possible with a massive team. So what we've got here is a team of experts in all the different areas that we're trying to simulate. So we have experts in embodied simulations and lensing, in galaxies, in CMB, and yeah, we're still looking to expand and simulate all the things in the universe, like line intensity mapping, etc. So very interested to collaborate with anyone who's interested. So yes, one fun thing we've done so far is measure the supersample covariance effect, which I'll talk about next. So supersample covariance is this effect where the universe is very big. We don't observe the whole universe when we go and measure it. We just measure some survey window. And so what this means is there's some fundamental scale which fits into this survey window, but any scale larger than the scale doesn't fit in the box, and so it's ignored in the analysis. And since 2013, 2014, maybe even before slightly, people have known that this causes an effect on the covariance matrix on the power spectrum. And so if you want to do a cosmological analysis, you need to take into this supersample covariance, take it into account. But as we move to higher order statistics, we also need to understand what kind of effect this has on higher order statistics. And so to do that, if you have a very big box simulation, as we do with HalfDome, you can split it into a bunch of little sub-boxes and measure your higher order statistic or whatever statistic you like in each sub-box. And this will include the long mode because it came from a large simulation which include this long mode. And then you can simulate a bunch of small boxes which are the same size as these sub-boxes, and because these are all simulated separately, they don't include this long mode. The longest mode is this small mode over here. And so by comparing the covariance between all these sub-boxes and the covariance between all these small boxes, you can quantify how big this effect is. And just to give you a quick idea of the simulation setup, we do classic EM, redshift 0. The big box size is 5 gigaparsec over H, the resolution 204A cubed. Sub-boxes are split into 8 by 8 by 8, so 625 megaparsec over H. And we look at the matter distribution and halos from friends of friends. And there's two ways you can define delta when you're doing this kind of supersample analysis. Delta equals rho over minus rho bar over rho bar. And you can choose to make rho bar either the rho bar of the local patch of the universe, so within the survey window, or of the entire universe. For lensing, it makes more sense to use the global, because when you do lensing, you're using a theoretical value of rho bar, and so that's the global value of rho bar. But with galaxies, you measure the number of galaxies in your patch, and that gives you the local average density. And so for galaxies, it makes more sense to use the local. But we looked at all of these different combinations. And so for the matter field, what we find is, so just to explain what these plots are, this top panel is the covariance matrix, the value, and then on the bottom is the ratio between the covariance from the sub-boxes versus the small boxes, so quantifying how big of an effect the supersample covariance is. And on the left, we're looking at power spectrum, halo mass function, void size function on the right. And you can see that for the global, let me my mouse. So yeah, for the global case, you can see that there's a factor 4 increase in the covariance due to this effect on small scales. And also for halo mass function, when you go to small masses, you have more and more halos, so short noise is smaller, and that means that the supersample covariance gets bigger as well, more important for small masses. For voids, interestingly, there's very little supersample covariance effect that's consistent with 1, probably because the abundance of voids is so low, they have such high short noise that the supersample covariance is not important in these scales. We also looked at the bispectrum, and here we find that there's not much of a supersample covariance effect for the bispectrum, looking at the equilateral isosceles and squeeze bispectrum. We also looked at the halo field. Here, both the local and global case have almost factor 6 increase from supersample covariance, K0.7. Halo mass function is the same plot as in the previous slide. Void is the same idea, still 1. And then in the bispectrum, now you can see that there's sometimes a factor 6 increase in the covariance due to supersample covariance. So what this is telling us is that as we move to include higher order statistics and do analysis with higher order statistics, we've got to take into account these effects, and our simulations enable people to calibrate the covariances and use the correct covariance. We also looked at the cross correlations between all the different probes. So if you do some combined analysis with power spectrum, bispectrum, halo mass function, void size function, what do all the off-diagonal components look like as well? And well, for matter, it seems like power spectrum, bispectrum is a very small effect. Moving to halos, which is closer to what we actually observe in reality, there's a big effect from all these off-diagonal components which need to be taken into account. So that's one fun thing we've done with these simulations, but not really what we intended to do with these simulations in the first place. What we have done is done some cool maps. We've got the matter density, velocity sheet, the mass sheet, the halo density. We've also produced a TSZ map and a lensing map. And there's more to come, and our first paper will be out soon, and there'll be a lot of fun physics to do in terms of CMP cross-access with these simulations.
What's the difference between like the bispectrum? You had like different Ks, like
Yeah.
K over 2,
Yeah.
etc. Like what's the significance?
I mean, so in general, you'd want to measure all different triangle profiles for the bispectrum, but that's extremely expensive to compute all the different triangles. So people typically just look at different regimes as a function of K. So if you just want to look at a one-dimensional plot as a function of K, you've got to say either look at the equilateral bispectrum, where when you change your triangles, you're keeping all the lengths the same, or you can look at KK2, which is an isosceles with half, and then the squeeze bispectrum, where one of the lengths of the triangle is basically 0. So yeah, I mean, ideally you'd look at all the different triangle configurations, but
These are just supposed to mimic all possible ones, like shapes, I guess.
well, not quite all possible, because kind of fixed one length to KO2, but this kind of gives you a good enough idea of what the effect is without having to do all the triangles. Okay, so that moves on to the next part of my talk, which is about field level inference. So kind of going to change what we're talking about more to the statistics side of things instead of cosmology, but apply to cosmology. And so I'm going to talk about doing field level inference with this new method with Microcanonical Langevin Monte Carlo. But I'll start by introducing field level inference. So before I showed you how high order statistics can provide information beyond the 2-point correlation function, but there's no guarantee that this gives you all the information in the field. Can we find all the information? So instead of just looking at these high order statistics, let's just find a general method to extract information from a field. And the way to do that is with forward modeling. So we know that in the L universe, everything was very Gaussian. So if you looked at an image of the L universe and you split it into pixels, smaller than these pixels, this is just an illustration, then you see that every point in your overdensity field is Gaussian distributed. Then you can evolve this initial field, which you call S, with some forward model, which could be some perturbation theory or n-body simulation, which takes in the initial parameters, the initial nodes, and the cosmological parameters like sigma A and omega m, and it gives you some final field, which could be the galaxy field or the weak lensing field. And the idea of field level inference is to take this backwards. So given what we observe over here, rewind the clock and reproduce the initial conditions of the universe, and also infer the cosmological parameters along the way. And because you're including everything that goes into the model of the universe here, so all the initial conditions and the cosmological parameters, this should give you the tightest possible constraints of cosmological parameters that you can get. And there's various ways to do this. You can use machine learning, you can use simulation-based inference, but the approach I've been using is actually writing out the posterior explicitly and doing inference on that. So given some data D and a forward model F, your posterior, which is a function of the initial modes and the cosmological parameters given the data, given by this likelihood term, where you have data D and forward model F, you try and match D to F, so you take D minus F, and then you have the noise term N, so it's just a chi-squared, and then you have some prior, which is saying that the initial modes are Gaussian distributed with variance given by the power spectrum. And then you sum this over all the pixels, and the challenge with this approach is that it's a multi-million dimensional parameter space. This S parameter, every single pixel in your initial field, is huge. There's a lot of pixels. And if you want to go down to the resolutions of upcoming surveys, it's going to be multi-million dimensional, maybe even billion dimensional parameter space. So in order to do this in practice, you need a fast forward model. You need to be able to evaluate F very quickly, and to get posterior quickly, you also want a differentiable forward model, because the techniques we use to do inference, like Hamiltonian Monte Carlo, require the gradients of the posterior, and you also need a fast sampler to get samples from this distribution quickly. So in terms of the first two, there's this code called PMWD, which is a very fast forward model and differentiable as well. It's written in Jack, so everything's done with auto differentiation. And this is able to simulate 512 cubed particles to do one n-body step in 0.1 seconds. So that's super fast and a really great way of simulating dark matter. This was developed by Yin Li, who was at CCA at the time. So this solves the first two problems, at least in terms of dark matter, and that's where I'll focus for the rest of my talk. And so question now I'm going to look at is, can we find a fast sampler to do this kind of field level inference? And that leads me on to microcanonical Langevin Monte Carlo. So the canonical HMC, so the Hamiltonian Monte Carlo, which most people are familiar with, the way it works is you have some, for example, one-dimensional probability distribution P of x over here. And in HMC, you introduce this pi parameter, this momentum variable, such that the joint distribution over x and pi is proportional to e to the minus h, where h is the Hamiltonian. And then you define h such that when you integrate out pi, so you marginalize over the momentum, you get p of x. And so that gives you some h, that gives you some Hamiltonian. And then given this Hamiltonian, you can follow Hamilton's equations of motion in phase space. And that will give you some trajectory, like over here. So say you start here, you move around at some constant energy. And you can do that to get samples in X. But the problem with this is if you just followed these constant energy contours, followed the Hamiltonian equation of motion, you wouldn't get accurate samples. So to get samples in HMC, you've got to take these jumps to different energy levels every few steps. And then in addition to that, so this is the momentum resampling. And in addition to that, when you take each of these jumps, there's an accept reject step, Metropolis Hastings accept reject step, which you've got to pass. And so sometimes you'll reject samples. And so this trajectory looks, this path in phase space looks quite messy. And so maybe there's a way to do this better. And that's what motivates microcanonical Hamiltonian Monte Carlo, which is a similar idea to HMC, but instead of doing this e to the minus h, you make the joint distribution proportional to the delta function of h minus e, where e is some constant energy. The reason this is called microcanonical is because this is the microcanonical distribution from statistical mechanics. And the idea here is that you can just follow some constant path, some path of constant energy, and get samples without having to do all of these jumps and accept reject criteria. Mathematically speaking, what this looks like. So in Hamiltonian Monte Carlo, what you have is this, here's the position here, u is the velocity. So these are the equations of motions that you have. In traditional Hamiltonian Monte Carlo, you just have du equals minus the gradient without the loss function. But in microcanonical Hamiltonian Monte Carlo, there's this extra piece, which just projects this gradient down into, this is a projection operator into the plane perpendicular to the velocity. And then there's this parameter which is dependent on the dimensionality. So the equations of motions are very similar. There's just this extra projection operator in MCHMC. And then to get microcanonical Langevin Monte Carlo, which is an improvement upon microcanonical Hamiltonian Monte Carlo, you add this stochastic piece to the equations of motion, which is, this is some random normal, and this is a tunable parameter eta, which tells you how big the randomness is that you add. And it turns out that adding this extra noise improves the ergodicity or the accuracy of the samples that you get. And so now that I've introduced the sampling method and field level inference, let's apply a microcanonical Langevin Monte Carlo to do field level inference. Just to tell you the setup that I'm looking at here, we have nonlinear dark matter with 1 LPT, 2 LPT, and 5-step PM. So we look at these different nonlinear configurations, look at 16 cube, 32 cube, and 64 cube. And the voxel size is 4 megaparsec over H. So we're really looking at the nonlinear scales, so all the way up to very high K. And we also inject some noise shown by this line over here. So this orange line is the power spectrum, this red line is the noise, and then the green line is the data plus the noise. What this looks like, so just to explain the process, we have some true initial conditions which gave rise to the final distribution of dark matter over here. We will observe some final dark matter, and we want to infer the initial conditions from this. And so when you run the sampler, slowly, it will start matching the final distribution to the measured final distribution and give you some samples of the initial conditions of the universe. And more quantitatively, what this looks like, so for the 32 cubed example with 2 cosmological parameters, this is a 32,000 parameter problem. You can look at the cross-correlation coefficient between the reconstructed field and the true initial field. to see how good your reconstruction was. And you can see that it's 1 on very large scales and then drops off as you move to smaller and smaller scales, and this is because of the noise. And then the transfer function, you can see is 1 all the way across K. So this is telling us that our samples are pretty good. And also very importantly, HMC and Microcanonical Langevin Monte Carlo give the same samples, telling us that both methods work equally well. But what's most exciting is that MCLMC is 22 times faster than HMC. So the process is really sped up by using this new sampling algorithm. And in terms of the cosmological parameters, so we looked at omega m and sigma A. Again, the contours look pretty much the same. But here, MCLMC is 42 times faster. So that's very exciting. And what's most exciting is the dependence on the dimensionality. So the ESS is the effective sample size, quantifying how efficient the sampling algorithm is. And you can see that the effective sample size for MCLMC compared to HMC is increasing as a function of the dimensionality. So as you move to higher and higher dimensions, the efficiency of this algorithm gets better and better. And so this is really promising, because when we want to do actual analysis of cosmological data, we want to go to maybe 512 cube to really extract everything. And so yeah, hopefully this method will really help us reach that point. Another fun thing about doing field level inference like this is if you want to do a joint analysis, for example, if you want to add peculiar velocities, you could just add this term to the likelihood. So say you measure some velocities v, you have some forward model for your velocities, like from an n-body simulation. You just add this term to your posterior, you do the same process, but with this new posterior, and you get different results, which include all of the information. I had a quick look at that. I had this for number density of 10 to the minus 4, and some velocity noise over 100 kilometers per second, and we found that along the line of sight, you get a slight improvement to your reconstruction in this regime. And so that would also give you tighter constraints doing an analysis like this. And if you get a higher number density or a lower velocity noise, then this improvement due to including velocities will get even better. And so moving forward, the dream is to use this approach to combine all the different probes from large scale structure and CMB, and use Microcanonical Langevin Monte Carlo to move up to 512 cubes and extract all the information from all the small scales that we're going to get from these new surveys. And yeah, so just to summarize, these are all the different components that I think we need to measure the neutrino mass as best we can. In terms of large-scale structure, we have galaxy surveys, redshift space, and peculiar velocities will be really important, and combined with weak lensing, Lyman alpha. One of the key challenges is modeling things accurately. So what I just showed you in terms of field level inference was just looking at the dark matter distribution, but that's not really what we observe. We observe halos and galaxies, and so making that connection between dark matter and galaxies, I think, is one of the key challenges in taking this forward. In terms of data science, we have field level inference, better sampling methods. You can also do likelihood-free inference, which is a way of getting your posterior without actually going through the process of sampling, and just generally using machine learning in terms of the CMB, cross-correlating with LSS, CMB lensing, and also improving the measurement of tau is very important. So that's very degenerate with neutrino mass. And then in terms of particle physics, that will give a cosmology-independent measurement which we can compare with. And that's the end of my talk. Thank you very much.
Any questions for Adrian?
I have a couple questions about the sampler. First, so you said you had this like stochastic parameter that was tuned. So is there like some kind of like optimization step when you have to do these kinds of
so in general, whenever you're doing sampling, you've got to tune some hyperparameters. And so in this case, you tune it at the beginning of some warm-up phase or burn phase where you tune this hyperparameter. So you basically, because you know that the energy is meant to be conserved in this microcanonical Hamiltonian Monte Carlo, you kind of just track the energy such that it's, once you know that it's constant, you know that you're using a good parameter for that.
Okay. And then the other question I have about it is that for like very vanilla methods like metropolis statings or even with HMC that have this metropolis project step, at some level you can be confident that you're exploring most of the parameter space, at least maybe in lower dimensions. Is there some assurance in these kinds of microcanonical methods that I would have like the same coverage of some high dimensional complicated posterior?
Sure. So dropping the accept reject step does essentially introduce some bias, but the way the parameters are tuned in the warm-up phase of microcanonical methods is such that they minimize the bias variance trade-off. So if you use too large of a step size, then yes, your samples will be wrong. But if you use a finely tuned enough step size, then the bias will be small enough that it doesn't matter. But you can also run microcanonical methods with accept reject to really get the guarantees that you would get in Hamiltonian Monte Carlo as well.
So of course, you're only measuring neutrino masses if you assume the standard model description of neutrinos. So, yeah, like you called the Catrin cosmology dependent, but it's also, I think, more particle physics independent. Like, are you interested in exploring other particle physics scenarios eventually?
Sure, yeah.
Like decaying neutrinos would be
say again?
like if neutrinos decay,
Yeah.
that would be an example where it'd be very different.
Sure, yeah. So these definitely will have effects on cosmology, but I think right now, just measuring mass is like the first order thing we can do.
Assuming the standard model.
Assuming the standard model, sure, yeah. So, yeah.
Going back to when you were combining different constraints from different higher order statistics, are these different higher order statistics independent of each other? Like, can you give me some confidence that it's okay to combine them?
Okay, so yeah, so you know that they're not independent of one another, but when you combine them, you include a correlation matrix, which takes into account the correlations between the different higher order statistics. So you have some, for example, if you assume Gaussian likelihood, you have your higher order statistics and combine them all with some covariance matrix, which takes into account all the different correlations.
Can you explain again that with the, you said you were data limited for the running the HalfDome sims, right? So, but it was extremely fast, whereas you're trying to optimize, you're trying to work, you know, for the time for the field level inference. So you're not data limited on that end, or what actually is the issue for, I guess, first of all, for the data bottleneck for HalfDome? Like, why can you not just get larger hard drives or move it off supercomputer? I mean, it doesn't seem like it's that much data, especially when, you know, Google and all these other companies, right, have tons of data.
Sure, I mean,
servers.
Yeah, so far for the field level inference, we're looking at a single redshift and we're looking at pretty low resolution, relatively speaking. So 64 cube and hopefully we'll push the 512 cube. So, but for HalfDome we have 6,000 cube number of particles. And also, in order to do CMB plus LSS, you want to save the entire light code. So all the information from particles at CMB, well, not all the way to CMB, but high redshift down to 0. And so that's a lot of data storage that you need. You want to store the halos as well, which doesn't take up that much storage. But in principle, what's taking up most of the memory is the particles in the light code. But you don't really care about all the particles in the light code. You can, what you care about is like the lensing observables. So if you had a way of just on the fly doing all the lensing, doing all the observable calculations, then you could throw away the particles, and this wouldn't actually take up as much space. We'd go up to maybe 30 terabytes if you threw away all the particles. In fact, now we're only saving 10% of the particles, and that's 300 terabytes. Yeah. So those are the main bottlenecks in terms of.
Great. And then you said, so with the current constraints, you could get down to like 0.02 EV.
Yeah.
Right. But what, and then for when you apply the field level inference,
Sure.
What are the estimates for that?
Yeah. So we don't have numbers yet. No one's applied field level inference to neutrinos. We have the simulations I showed at the beginning, which suggest that there is information beyond just the power spectrum from all the higher order statistics. And so yeah, looking at the matter field look really promising, then looking at the CDM field look less promising. And so yeah, it's now a work in progress to figure out exactly what the number is when you go to the real observations. But yeah, the forecasts for now are around 0.02 EV based on traditional methods with CMBS.
Any other questions for Adrian? Not, sing him again.